Hi everybody, thanks for coming back from the lunch break. We were asked to speak in English because we found, I think, at least one person that doesn't understand Hebrew. So I'm from the Department of Marine Technologies in the School of Marine Sciences in the University of Haifa. I'm establishing a new lab in a new department. So I'll take 5 minutes and give you an overview about the vision of our new department, the global context of the department, and then I'll present a couple of my recent works that are related to computer vision. So if we look at the Earth, there is a famous saying by Arthur Clarke, the writer. He said how inappropriate to call this planet Earth when it's quite clearly ocean. And indeed, when you look at the numbers, so 70% of the Earth's surface are covered by ocean. In the volume, it's even more. And if you look at life, it's 50 to 80% of life on Earth in the ocean. And every kind of, more or less every statistics, the ocean has is controlling our planet. And it has a great influence about our life. So I have here kind of 6 examples. The upper 4 are more, I think, obvious and trivial. I want to emphasize the 2 bottom ones. One is that 50% of the photosynthesis on Earth actually occurs in the ocean. So when you think about the rainforests and all that, they're very important. But a similar amount of photosynthesis occurs in the ocean. The reason it's more surprising is because it is done by microscopic organisms. So it's not that we see forests in the ocean, but there are plenty of microscopic organisms that accumulate to roughly the same area. And the second thing is the ocean has at least 50% of life on Earth, and it has distinct proteins. It's a home for biodiversity. And my favorite example is what you see here. It's called GFP, green fluorescent protein. That's a fluorescent protein that was found in jellyfish, and since then has changed the world of biomedical imaging. Scientists use it in microscopic imaging to paint cancer, for example, and other brain cells and so on. And then all this protein comes first from jellyfish, then they found it in corals. So all this came from the ocean. And in Israel, so if you look in Israel recently, there is a lot of talk about the ocean because of the gas drillings. And indeed, if you look at the map, this is the map. This area is called the Exclusive Economic Zone of Israel, the EEZ. There are rules, international laws about it, but if you look at the area of the EEZ of Israel, it more or less doubles the area of Israel. So all the resources we have land, we have the same amount in the ocean, and we have the recent gas drillings, and also there are plans to move the airport to the ocean. I don't know if you know about that. And at Back 2020, desalination plans, and so on. Now, if you look at what do we know about the ocean, so it's amazing to realize that only 5% of the ocean floor has been seen by eyes or cameras. And there are estimates that at least 50% of the species are still undiscovered. And these are recent examples. By the way, I talked about fluorescent proteins. These are new fluorescent proteins that were discovered last year in fish. And if you look at Israel, now we have more work in the ocean because of the gas drillings. So this is an example of a Roman jar that was found near the Tamar drilling 3 years ago in the depths of 1,700 meters. And this is a new ecosystem, a new biological ecosystem that wasn't known until 3 years ago. This is at the depths of 700 meters off shore of Palmachim. And I recently, this is a long sentence. I was doubting whether I want to show it or not, but I think it's interesting. And I heard it in a talk about deep sea research. And that's a quote by Donald Rumsfeld. He said, let's see if I, if I can read it correctly. There are no knowns. These are things we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns. The one we don't know, we don't know. So, okay, I hope I didn't make a mistake. But the point here is that this was quoted by a deep sea biologist, and this is the feeling among the deep sea researchers, that there are unknown unknowns. Now, I Googled it, and you can do it too. Donald Rumsfeld was the Secretary of Defense in the state, and he said that about the war in Iraq, which is quite scary. But I think it's interesting for us, and also in science, to realize there are unknown unknowns. So realizing that there is a global trend in the world, and also in Israel, that my department is part of, and the realization that we need to put more effort into studying the ocean. And this needs new technologies. The ocean is a hostile environment. We can't just go and look what's there. We need novel technologies. And in the world, and also in Israel, there are more resources put into that. By the way, if you look at research of the space, so in the states put 150 times more money in the research in NASA, researching the space, than in the ocean, which is, I think, affecting our life more. So the School of Marine Sciences in the University of Haifa received a nice donation to open our new department. And the plan is to build a center that will have facilities for deep sea research and marine technologies research. So I'll briefly explain you what you see. What you see here, it's called an AUV, an autonomous underwater vehicle. That's an autonomic submarine. You can send it, program a plan, and it will go swim in the ocean and will come back with data, either images or bathymetric data. This is an ROV, remotely operated vehicle. This is also a robot, but it's connected with a tether to the boat. This is a boat that the Oceanographic Research Center got from the Navy, so it's now being renovated to be able to take these vehicles out to sea. And what you see here, this is in Haifa. It's not part of the University of Haifa. It's the building of the Israeli Oceanic and Limnological Research Institute, but we will be there. We are now constructing our new lab space and the new department space there. And we will have there our own labs and also a center for these vehicles, a test pool, and so on. So real facilities for ocean research. And these are the planned labs. These two, this is mine. The other two, we are already establishing these. And the next one will be next year. Okay, and now about my research. So I said there are still things we don't know about the ocean. And in this context, when we look at cameras and computer vision algorithms, these provide us the eyes to see what we can see by ourselves. You saw the research happens when we send robots out there, and then the information they bring us, this is the information we have, and we need to extract as much information as we can from there. So when you work in the ocean, many computer vision algorithms won't work, either because of many challenges, either visibility problems, attenuation, scattering, color changes, refraction, movement, and also just when you imagine the large volume of the ocean, if you want to cover it, you need to do it wisely. And this is the goal of my research, to develop novel algorithms and imaging systems for ocean science. And I concentrate on building systems and algorithms that will work in situ. And here you see a few pictures of me deploying some of the systems I worked on in the past 4 or 5 years. Okay, so now I want to show you two different works, recent works that are related to that. First, I want to talk about photometric stereo. So this is not underwater, that's conventional. This is just a fast reminder of what is photometric stereo. We want to reconstruct a 3D surface. What we want, photometric stereo uses one viewpoint and 3 different light source locations. From these, we get 3 equations. We can extract the normals. The normals are 3 unknowns. And then when we have the normals, we can reconstruct the surface of the object and the 3D surface. If you look at the assumptions of the conventional photometric stereo, we have distant light sources, known directions and intensities. There is no medium, and the surface is Lambertian. More or less, most of them, we don't have them in the water. And just, I won't go over all what's going on, but We have the light is attenuated by the water, and we have scattering by the medium. The light is scattered in the forward direction, but also it's scattered back to the camera. So if you look at all that, think about what we want to do. We want to use the changes of the intensity of light because of the different light source positions to reconstruct the normals. So we want to extract data from the change of intensities of the light, but the medium also changes the intensity of the light. So we need to take that into account. And furthermore, we want to reconstruct the shape of the object. So the shape changes the distance of the points of the object from the camera. But the water effects, if you can see it here, they also depend on the distance of the object. The attenuation is distance dependent, and so on. So the water effects depend on the unknowns that we want to reconstruct. So let's simplify the problem. Let's assume we don't have scattering at all. We only have attenuation. I won't go into all the details here, but it turns out you can plug in the attenuation into the equations and then have an equation for the normals that depend on the distance of the object. To solve that, we need 4 equations, so one more input image. But now I assumed there is no scattering at all. Let's see what happens with the scattering. First, forward scattering causes blurs the light. So it blurs the light when it goes from the light source to the object, and also when the light comes from the object to the camera. Now, when we look at the light source blur, this is critical because we wanted to look at the intensity of the light reflected from the object, based on knowing where is the light source and what's going on with it. But the medium changes the light source, it blurs it, and then if we calibrated the direction of the light source, we're not sure it's the same direction anymore because everything was blurred and we don't know what happened to the intensity. So we performed simulations, but it's also, I think, intuitive. When the light source is symmetric and the blur function is symmetric, it turns out for small scattering angles, the direction of the light source doesn't change, and then we can assume the light source is coming from the same location, but the intensity changes. So this needs to be calibrated. And another effect is backscatter. Backscatter is light that is scattered by the medium towards the camera before reaching the object. As you can see it a bit here. It veils the object. In this work, we assume we work with fluorescent objects, and then because they fluoresce, the backscatter is removed, as you can see here. So I'll show you results. If you look at, so this is the setup we used. It's a fluorescent mask. This is still in the tank in the lab. This still didn't go into the ocean. There are a few more steps needed to do that. So we have, this is the object in water. You don't see the water because the water is clear. And you have a camera and light sources pointing to the object. This is how it looked like when we actually made the water turbid. And what you see on the left are the 4 input images we're using, and the result using the standard equations. And when you look at our method, these are the input images, and you see we got a nice symmetric face and not a scary face as in the left. And what's nice is when you increase the turbidity of the water, you can see that the top row is our results. They're stable. What you see is the blur affects the resolution of the reconstruction of the details of the mask. But the bottom row, it gets more asymmetric and with less details. Okay, now we'll switch to a different topic, which is in situ underwater microscopy. So I said there are plenty of things in the ocean, and usually if you think about the ocean, it's big and so on. But it's full of microscopic organisms that are important. I told you about the photosynthesis. This is the photosynthesis is done by microscopic organisms, the ones that you see here, plankton, you think about corals, or the animal is microscopic as well, and we also have many particles, that is, it's important to measure an image in situ. And what are the difficulties in that? Imagine, I don't know when the last time you used a microscope in the lab, but usually what would you do? You take the sample, put it on a nice plate. Usually biologists kill the organism before they put it, so it doesn't move on the plate. And then you put it on the plate, and then you can gently focus the microscope and get the images. When we do it in the water, the goal was to do it on live organisms and image the natural setting. So no killing, nobody, and no fixing. Everything is moving, and we still need to focus everything. Now, I'll show you a microscope with a resolution of 3.4 microns per pixel. So each pixel images a size in the world that is 3.4 microns. This means that if during the exposure time the organism moved more than 3 microns, then it results in motion blur. So we have to overcome that and have very short exposure times. So this is the first microscope I worked on. This is doing bright field imaging, and from I don't know if you can see it well here, but the optics are composed of two housings. One has a camera and one has illumination. The illumination illuminates into the camera, and this gives us what's called bright field imaging. And you can see examples here where we don't have an organism in the field of view. The image is bright because the light passed, but when we have an organism in the focal plane, it attenuates the light and then it appears dark. And what you see here is images we took in situ in the ocean. You see me here with the microscope in the high sea. I think you can see that it was a high sea. The microscope is deployed from the ship. Everything, the boat was moving, the microscope was moving, the organisms were swimming, but we still managed to get the resolution you see here. And what we did here, we didn't actively focus on the organisms, but we had one focal plane, and the organisms swam through, and then in some frames we got them in focus. But then we said we want to image corals, and this is the drawing that was before the project. This is what we dreamt about doing, and I'll show you that it actually worked. We want to do microscopic imaging of corals. The corals won't swim into the focus, but they also move. They have tentacles that move. And I'll show you the microscope we built. So first, I don't know when was the last time we went diving, but when you look at corals, they look more or less like that. Also in regular images, when you zoom in, you see small circles here. These are the coral animals that compose the coral. Here they are blurred because they weren't taken with our microscope. But now I'll show you what happens there, really happens there. And I'll show you a movie that shows a time lapse where we place the microscope looking at two corals in the ocean. This was in Eilat. And this is the setup. So two corals, the microscope is looking at them. But before, I want to say a few words about what's special about the optical design of the microscope. So first you see the ring illuminator. This is specially designed to focus the light to achieve high intensity of light. So each LED there is focused by itself, and all these are focused together into the focal plane. And the more interesting part is an electronic focal lens we used that can electronically change using that, we can electronically scan the focal plane of the system. Okay, any guesses of what's going to happen now? I'll show you. So the field of view you see here of the full image is 1.7 millimeters. Try to do it with your fingers. It's pretty small. And here you see one polyp. That's the coral animal. And on the right side, the second one, that's a different, that's the other species. And what's happening, if you're guessing, is that they're fighting. They're fighting over space. And you can see they're slowly reaching their tentacles. And also what you see here, which is now out of focus, but will come back into focus, is it's called the mesenterial filaments. These are the digestive filaments. So they try to eat each other, more or less. Yeah. So I think I have still, the movie is longer, but I have another minute or so. So we'll watch that. And just a few note here. This is how the microscope looks like when we are diving. We have a diver interface. We built everything by ourselves. And then because we have the electronic lens, the diver can actually focus the microscope using the interface. Yeah. And the small brown dots that you see here are symbionts that live in the coral, and their size is more or less 10 microns. So this is more or less the resolution we achieved. And I think I'll leave you in suspense regarding who won. But I think I need to finish. So, okay. So to sum up, we have new activities, and you saw it ranges from computer vision algorithms to building imaging systems. This is, by the way, a curious fish that came to see his reflection while we were doing an experiment imaging corals in Eilat. So this is my camera looking at the corals. I was trying to take a picture. It didn't focus because the fish came in to look at its reflection, but my body took a picture of him. So we have a new lab and a new department. We have an opening for a lab engineering and research assistant, and also a spot for graduate students and postdocs. Thanks.